Hey Royals, in today's lesson, we're going to look at the efficiency of energy transformations. So on your page right now, you see two bouncing balls, or the picture of two bouncing balls. What I want you to do is I want you to pause the video right here and determine which of the two pictures on your screen demonstrates a better efficiency. So the energy I put into the system, ET1, should equal the energy that comes out of it, ET2. So that demonstrates to me something that is very efficient. So it's getting the same amount of energy out that was put into it. Now the same thing can't be said about our second picture. You can see that this total energy line seems to be decreasing as we move from left to right, which means that energy is being lost to the system, being lost to the surroundings. Right? So this demonstrates an object that is not very efficient. It's losing energy, or it's getting a different amount of energy or lower amount of energy out than what I put into the system. So what I want us to do right now is I want you to look at this series of bouncing balls and demonstrate the energy transformations that are occurring. So again, pause the video, see if you can write the energy conversion for these bouncing balls. So I've written the energy transformation equation that I believe is occurring in the first picture. It starts with some type of gravitational potential energy due to the fact that the ball has a height, and as it starts to fall, I get kinetic energy plus gravitational potential energy. At the very bottom, it has elastic potential energy, and then it transfers back into kinetic energy and gravitational potential energy, and then finally back to gravitational potential energy before it does the same process over and over and over. This is a perfectly efficient 100% of the energy that I put into the system comes back out of the system. So I'm not losing anything to the surroundings. However, in the second case, I might say it slightly differently. I would say that originally it has gravitational potential energy. It's transferring into kinetic plus this gravitational, but as it comes to the ground, maybe the ball's making some noise as it strikes the ground. So I'm losing energy due to thermal energy. And so I'll say that at the very bottom here, that's the case for us getting some type of thermal energy in our second case. So as the ball starts to rise back up, it transfers back into gravitational potential energy, and then finally back to our gravitational potential energy, but it is lower than it was at the very beginning. So how do I actually calculate this? Efficiency can be calculated as the ratio of the output energy or the useful energy to the input energy, or the amount of work that I put into our system. And then I multiply by 100% to make it a percentage. And it should be noted that in most cases, I would say 99.9% of cases in our universe, the energy efficiency will never ever be 100%. You're never going to get the amount of energy out of the system that you put into the system. And it's because of things like friction, thermal, light, sources of energy that could be dissipating from our system. Okay, so what I want us to think about is the input versus the output energies. So this is pretty much the hardest part of calculating efficiencies, is identifying the input energy compared to the output energy. So I have an example here where it says an electric car drives down the highway. In that case, the input energy is our electric energy. It comes from the batteries. And then the output is the kinetic energy that causes my car to start to move. So what I want you to do, again, pause the video, see if you can identify the input and output energies for the rest of these transformations that are occurring in this table. So welcome back. So I've filled in the table here. So I would say that a ball being launched from a slingshot has elastic energy being stored in the ball as I stretch the material. And when I release that energy, that's the energy being transferred into our useful energy, and that's kinetic in this case. For the next one, with the roller coaster at the very top of a hill, it has an input of gravitational potential energy. However, as it starts to move down the hill, the useful energy or the output energy here is kinetic energy. In the last case, when I have a gas furnace, the gas furnace is driven by our chemical energy in the natural gas that would be in the furnace, and it's producing thermal energy, that heat that you have inside your home. So that's the output energy in that case. So that fills in the rest of this table. Let's actually go through a couple examples together on how we calculate efficiencies and how we determine an input energy versus the output energy. Okay, so the first example here, I have a 48 kilogram box that's being pushed up a ramp, and the ramp is 4 meters long. So I'm going to just draw it here at the top of our page now. And this is essentially the situation that we have. And the ramp is 4 meters long. And I'll draw my box here. There's my box, and then it comes to the top. And the distance that it's going to travel, we're told, is 4 meters. And the force that I'm applying is 178 newtons. Now I'm applying it straight on the box. So the force is being pushed straight up the hill, and so is this distance that the box is moving. So the angle between the force vector and the displacement vector should be 0 degrees because I'm pushing the same direction that our box is moving. At the very top, it has a height relative to the ground of 1 meter. So it's going to gain gravitational potential energy as it goes up this ramp. So we want to determine the efficiency of this ramp. So the input energy, the energy that I put into the system, is based on the work that I do on the box. So I want to determine the work on the box, so the applied force multiplied by this displacement or distance multiplied by the cosine of the angle between this displacement vector and our force vector. Okay, so let's calculate that. The applied force is 178 newtons. The distance that the box travels is 4 meters. And the angle between this force vector and displacement vector, we've already discussed, is 0 degrees. Working this through, I get a work value of 712 joules. That's going to be my input energy. The input energy into my system is 712 joules. So once it gets to the top of the hill, it has gravitational potential energy, which means that the output energy that I could possibly get from putting a box at the top of the hill is based on just gravitational potential energy. So that will be mgh. So our box is 48 kilograms. Gravity is 9.8 meters per second squared, and the height is 1.0 meters. And if I multiply this all through, I get 470.4 joules. So my input is larger than my output, which tells me that this ramp has a efficiency that is less than 100%. So we can go ahead and calculate the efficiency. So I can say the efficiency is the energy out of my system divided by the energy into the system multiplied by 100%. And if I put my output energy of 470.4 joules divided by my input energy of 712 joules, multiply that by 100%, I get a value of about 66%. So I know that my efficiency of our ramp right now is 66%. So that is an example of how I can determine the efficiency of our inclined plane. So let's look at a problem that deals with a motor. So a motor on a train, and this train is going up a hill, so I'll draw something like this. And my hill has a height of 55 meters, and I'll draw my little train up here. There's my train coming over the little hill. As it's gone up over that hill, I'm storing gravitational potential energy in my train. And we're told that the efficiency in this case is 75%. And my mass of my train was 2,400 kilograms. So we're asked to determine how much energy does the motor need to input so that I can get this train to the top of my hill. So if we use our equation for efficiency, which states that it's the output energy divided by the input energy multiplied by 100%, I need to first determine my output energy of this train. And it's based entirely on its gravitational potential energy. So the output energy here is mgh. So I'll substitute in 2,400 kilograms multiplied by 9.8 meters per second. And I multiply that by a height of 55 meters. And I get a fairly large number. I get 1,293,600 joules. Okay, so now I know I can calculate my input energy because I know the efficiency, I know my output energy. The only thing I don't know is my input energy. So I'll write down 75% is equal to output 1,293,600 joules divided by my input energy multiplied by 100%. So if we divide 100% on both sides of my equation, I get 0.75 is equal to this output energy divided by my input energy. And rearranging my equation a little bit, I can find out that the input energy is going to be equal to my output energy divided by 0.75. And when I do that, I get a value of 1,724,800 joules. Or more importantly, I can just write it as 1.7 times 10 to the 6 joules. And there we go. We've gone through an example where I can determine the efficiency, the input energy, knowing our efficiency. So in this lesson, we identified efficiency, what we mean by efficiency, and how we can use energies to determine the efficiency of different machines or situations. So if you have any questions or concerns about this lesson, please don't hesitate to reach out to me.